So let's look at function operations. What I want to have is a function f and a function g, and I want to combine those in some way, okay? And the result of this operation is actually another function, which I'm going to call h here, okay? So that's what I want. I just want a way to combine things to generate new functions. Now, remember when we did this with relations? Relations are sets. And so all of the set operations like union and intersection and set difference actually apply to relations. And the same is true here. Functions are relations, which are in turn sets. So any set operation, any relation operation is almost automatically a function operation, right? The only problem is that we need to make sure that we actually return a function. So if I take, for instance, the union of two functions, I don't necessarily get a function because functions have that restriction that you can't have two y's that are associated with the same x, right? So as long as the resulting set is actually a function, then any set operation or any relation operation for that matter will actually be also a function operation. So let's take a look at some examples. Let's take at f union g. When is f union g a function? And remember, it just needs to have the function property, right? So there's only one y associated with hx. And one thing that means is that, well, I should say the easiest way to make that happen is the domains of f and g are disjoint, okay? That means that there's no intersection, so there's no way when we combine them to actually have a problem where, some x now has two different y's associated, one because of f and one because of g. X is in one or the other, but not, okay? So that just doesn't happen. So that's good. That's one answer, right? A slightly more general answer might be this. It's okay if the domains overlap, right? As long as the values of the functions f and g agree on that overlap. So here's kind of a classic function that is defined as a union, right? So we have two functions, minus x with the domain x less than 0 and x with the domain x greater than or equal to 0. Take the union of those functions and you get the absolute value function, okay? So this strange notation, this is by cases, right? When we define a function by cases, is really union. And we just have to make sure that any kind of an overlap results in the same answer. Okay, so that's unions, right? And things like intersection and other set functions like or set operations like set difference, I'm going to let you think about whether those result in functions and when they result in functions. Okay, so let's look at another operation. This is a relation operation, f composed with g. We actually already know what that is. That's because the composition is defined on relations, right? So f circle g or composition g is already defined, okay? That's important to know because I'm not actually giving you a definition of this, okay? But what I will do is I'll tell you what is equal to in terms of functions. So what we have is that f of g of x is actually f of g of x, right? Now, I want you to back up and remember the formal definition of composition in the context of relations. And you'll find that it's actually equal to this because of the function property, right? Now, why is this actually a function? Well, it always is because of this. F of g of x, well, the first thing I need to do is find some y that is associated with x because of g, right? But there's only one such y because g is a function. That's what it means to be a function, right? If you know what x is, then you apply the rule and you get g of x, okay? So now there's only one y, and I give that to f, right? And f of y, it's just one thing, z, okay? And it's only one because f is a function. So f of g satisfies the function definition. For each x, I actually get only one possible value of the function, okay? Now, here's some examples. F of x equal x squared, g of x equal to sine x. So f of g is, well, first I apply g, so x becomes sine x, and then I apply f, so we square that, sine squared x, okay? G of f, on the other hand, first I apply f, so x becomes x squared, and then I apply sine, so I end up with sine of x squared, okay? If I do g of g, then I have sine of x, right? Because I apply g twice. If I have f of f, then I get x squared squared, which is just x to the fourth. So that's just the way that composition works. I do want to make a kind of a notational distinction that's important. Okay, when I talk about f circle g, this is actually a function. Okay, so I might actually write it down. I rarely will, but I could write it down like this: 1 comma 4, 2 comma 5, and so on, right? I mean, I can actually, it's set, it's a function, so it's a set. It's actually a relation, so it's a set that contains order pairs, where, you know, the first element in the order pair comes from the domain, and the second one comes from the codomain. Okay. On the other hand, when I write f of g of x, what I actually have is a number if x is known. So f of g of 3, well, that's some number. Okay. If x is a variable, right? If we don't know what x is, then f of g of x is actually a rule which says how to compute f composition x, or f composition g, or f circle g. Okay. So make sure that you realize that some of these are functions and some of these are numbers. Okay. And here actually is how I would write that, you know, so I could spread it out as a set. Okay. Now, I talked about the domain and the range. So what exactly is the domain of this? Well, it has to be the domain of g, because f of g of x is equal to f of g of x, right? So to compute g of x, x needs to be in the domain of g. Right? There's just no other way. Okay. Now, what about the codomain? Well, the codomain is the codomain of f because it's f of something, right? So it's got to be in the codomain of f. So again, you know, just I mean, these are little details, but make sure that all of this makes sense to you. Okay. Last one that I want to cover here is f inverse. Okay. Now again, f inverse is already defined. And why is that? Because we did it in the context of relations, right? This operator is defined for relations. So I can tell you some things about f inverse when f is a function, but I already know what f inverse has to be. Okay. Now, what exactly is the inverse of a function in its own right? The answer is that only happens when f is 1 to 1. Okay, because what exactly? Let's say that I know that f inverse of x is equal to y. That means that f of y is equal to x. Why? Because xy belongs to f. That means that yx belongs to f inverse, right? I mean, that's what we do when we do inverse of relations. Okay, so why do I know that there's only one x associated with each y? Because it's 1 to 1, right? That's what it means to be 1 to 1. So actually 1 to 1 functions are the only ones that you can invert. Okay, take x cubed. F of x equals x cubed. We know that's 1 to 1. That means that f inverse of x is actually the cube root of x, right? And look at x squared. Then f inverse of x is actually not a function, okay? Because f is not 1 to 1 over the reals, right? Some people will say, oh, wait a minute, it is a function. It's actually plus or minus square root of x. That's not true. It's plus or minus square root of x. That means there's two values associated with each x. Again, not a function. Okay. Now there is a way to actually fix that if you need to. Okay. So suppose that f of x is x squared, and I really want to have an inverse function. So what I'll do is I'll say, look, just look at the non-negative reals. Okay. If you look at the non-negative reals, then f of x squared, actually is 1 to 1, right? And another way of saying that is that for each x that is non-negative, right? Or rather for each y that is non-negative, I can only find one non-negative x such that x squared is equal to y. Okay, so yes, f is 1 to 1, and that means that it has an inverse, and that's what we call the square root. Okay, so we take the inverse of functions that are not 1 to 1 by restricting the domain. And if you can remember your trig, then you'll remember doing the inverse functions for trigonometric functions, and that was what we kept doing, right? I mean, it's like, oh, so the inverse of sine is always between minus pi over 2 and pi over 2. That's because over that range, sine is a 1 to 1 function. Okay, so let's talk about domain and codomain of inverse functions. Actually, I think you can pretty much guess this. The domain of an inverse function, you can think of it as either the codomain of f, right, or just the range of f. Okay, if you pick the range of f, then every element of there is actually mapped by some value in the domain, which means that our function is total, right? For any x, f of x actually really does exist. On the other hand, if you pick the entire codomain, then it's possible, you know, unless the function is onto, that we pick a number and it doesn't have an inverse. So f inverse of that number doesn't exist. And here's a simple example of that, right? What is the square root of -1? If we say, right, that we're restricting x belongs to 0 to infinity, right, the non-negative reals, right, it's still the case that we don't know what the square root of -1 is, right? So because this is supposed to be in the range, which was all the reals. If you restrict yourself to, or rather the codomain, which is all the reals, if you restrict yourself to the range, which is the non-negative reals also, then we wouldn't have a problem, right? We couldn't ask for that because that's not a non-negative real. But if we don't take care of talking just the range, then you end up with what's known as a partial function. And this is just like partial orderings, right? A partial ordering is one that doesn't order every two elements. So sometimes it simply says, no clue. A partial function is like that. It doesn't map every x to some y. Sometimes it says, oh, geez, I don't know, right? If it isn't a partial function, then we call it a total function, which means that every x has a y that it's associated with. Okay. As far as codomains, that's just a domain. That one's actually easier, right? So let's prove what I consider to be the fundamental property of inverse functions. And this is something that you're probably familiar with. And what we have is that f of f inverse of x is actually equal to x, right? That's the fundamental property. Now, I can't just say that for all x, right? I have to have this qualifier that says that f inverse of x exists. And when does f inverse of x exist? Well, that's when x is actually in the range of f, okay? If x is in the range of f, then there is something that maps to it, right? And when I take that something and I take f of that, I should get x, right? That's what I mean by inverse. So let's go ahead and prove it. And this will give you some practice on how to use the definitions here, okay? So let's say that y is equal to f inverse of x. So what does that mean? Well, what that means is that x comma y belongs to f inverse, right? Because that's exactly what this notation is. Something is equal to f of something. Well, that means that that pair belongs to the function, right? So here we have. Now, f inverse is simply the function that reverses the elements of an ordered pair. So since xy belongs to f inverse, then that means that yx must belong to f, right? And in particular, that is exactly the same thing as saying that x equals to f of y. Because again, that's just the notation. We say something is equal to f of something if that ordered pair exists in the function. Okay. So now if we look at f of f inverse of x, which is what we were interested in, this thing here is actually y, right? And f of y, we know, is equal to x. So there it is, right? So that's the end. That's the proof, right? It's pretty straightforward. You just got to kind of open up the definitions and just keep driving. And that's a message that I keep trying to give you, right? That's the way that we do proofs. Yes, we have the propositional reasoning. We have the quantifier reasoning. We get really good at those because those we're going to need all the time, right? And then once you have that, it's just a matter of opening up the definition so you can prove things about the specific things that you're interested in, okay? Okay, so here are some others that you should be able to do for practice. F inverse of f of x is actually equal to x. This seems perfectly reasonable, right? So what you're going to need to do is follow something that is very similar to this, okay? And the only thing that you're going to need to find is what exactly is this restriction, right? Because when I say f inverse of f of x, maybe I need something like this so that the statement makes sense, okay? Here's another property that you should be able to prove. So this is kind of number one. And this is number two property that I want you to prove. The inverse of a function is actually the original function, right? I think you'll find that that's really, really easy to prove. Okay. All right. Let's move on to another way to build functions. Okay. And this way is something that we really didn't do for relations. This is new. And this is to define functions kind of by pairwise operations, right? So what I have is some relation. So some function like plus, minus, times, divide. Okay. All of these are binary functions, right? Or operators, right? You can think of it as arithmetic operators, right? And what I'm going to do is I'm going to define f plus g, for example, right? Where I'm applying one of these operators. And this, I need to emphasize, is a function, okay? So think of it as a function that has a funny name, right? F plus g. And I'm defining it by saying that f plus g of x is simply f of x plus g of x. Okay, and notice that f of x is a number, g of x is a number, which means that this is just the addition operator that we learned from kindergarten, okay? Right, because we're just adding two numbers. This is not the addition operator. Okay, that is just simply a name, right? I'm just telling you what the function f plus g is, right? And because I can't actually add the functions, you know, I can't add f and I can't add g. They're sets. They don't have addition. Okay. So anyway, when exactly does this make sense? And f and g have to have the same domain, because in order to complete f plus g of x, I need f of x and I need g of x. So they have to have those domains, right? And again, they have to have the same codomain, because what am I going to do with f of x and g of x? I'm going to add them, right? So they better be kind of in the same space. And the codomains have to be numeric so that I can actually add, right? So this really only makes sense for kind of numeric functions. You can see that I could generalize this to non-numeric functions as long as I can do something pairwise to the elements. Like, for example, if I have functions over lists, then I could do something like concatenation of lists and do the same kind of trick. Okay.